Today I'll be talking about acid, bases, and nucleophiles. You must be aware of the Bronsted-Lowry concept of acid, which states that an acid is a proton donor. So consider an organic molecule Ha. The acidity of the proton will depend on 6 factors. The first factor is the electronegativity of the atom bonded to the proton. The second factor is the S character of the CH bond. Electron withdrawing inductive effect of the substituent also plays an important role in the acidity of the proton. The size of the atom attached to the proton is important. The fifth factor is the steric hindrance in the organic molecule. And the last but most important factor is the delocalization of electrons by resonance in the anion that's formed after the loss of proton. We will cover each of these factors. The first factor is the electronegativity of the atom that is bonded to the proton. Let's consider the atoms that are labeled in red: carbon, nitrogen, and oxygen. The electronegativity of carbon is 2.5, of nitrogen is 3.0, and of oxygen is 3.5. So as the electronegativity of the atom increases, the acidity of the proton attached to these atoms also increases. And this is evident from the pK values observed. For example, methanol has a pK value of 16, and so it's the most acidic. Remember that lower the pK values, more acidic is the compound. Let's look at the second factor, which is the S character. The 3 molecules we'll be considering is methane, ethane's 1 double bond, and ethyne, which has a triple bond. In methane, the S character is 25% because the carbon atom is sp3 hybridized, whereas in ethyne, the S character is 50% because the carbon atom is sp hybridized. And because of that, the pK value of the proton on ethyne is 25, whereas the proton on methane is 50. Let's consider the next factor, which is called the inductive effect. So what is inductive effect? Inductive effect is the ability of an atom or a group to pull electrons towards itself, and it's represented by -I. Here is a list of atoms frequently encountered in organic molecules with their electronegativity numbers. The factors that affect the inductive effect is the number of electronegative atoms. Let's consider a simple example: acetic acid. The pK value of acetic acid is 4.8, and it has a methyl group. If we start replacing the hydrogens on the methyl group with chlorine atoms, the pK value keeps decreasing. For trichloroacetic acid, the pK value is 0.6, and it's pretty acidic. The next factor is electronegativity of the atom. We'll consider the example of acetic acid. Here you can see that the electronegativity of the atom that's attached to the carbon keeps increasing as we move from bromine to chlorine to fluorine. The last factor is the distance from the carboxyl group. So in this case, if the electronegative atom is attached to the alpha carbon, then it has the maximum inductive effect. If it is attached to the gamma carbon atom, it has very little inductive effect. So closer the electronegative atom, higher the inductive effect. So these are the pK values. As you can see, when the substituent is on this alpha carbon, the pK value is 2.8, but when it's on the gamma carbon, the pK value is 4.5, which is pretty close to that of acetic acid. Increasing the acidity and size of atom. So here there are examples of hydrogen halides, starting from fluorine and going to iodine. You can see that fluorine size of the atom is the smallest and the size of iodine is the largest. What that means is the pK value of Hi is the lowest and it's most acidic. Let's move on to the next example, which is acidity of steric hindrance. Consider the example of propanol. It has a pK value of 16. If the branching increases, as in case of isopropanol, the pK value increases to 17. Steric hindrance or the branching increases, then the pK value increases to 18. So as you can see, with the increase in steric hindrance, the pK value increases. That means the proton becomes less acidic. Let's move on to the last factor, which is resonance of the anion. For this, let's consider ethanol molecule. The anion of ethanol does not have any resonance structures. pK value of the proton in ethanol is 16. In case of phenol, the pK value is 9. And the reason for this low pK value is because the negative charge on oxygen can be delocalized into the benzene ring. And you can draw a lot of resonance structures. Let's look at acetic acid. In case of acetic acid, the negative charge can be delocalized on 2 oxygen atoms. Since oxygen is more electronegative than carbon, it can manage the negative charge much better. And hence, it has a lower pK value than phenol. In which case, in phenol, there's only 1 oxygen and the delocalization of electrons on the carbon atom is less effective than that in acetic acid. In case of benzoic acid, again, there are 2 oxygen atoms and there's delocalization of electrons here. So this particular slide shows all the examples of different types of acid. Let's start with strong acids. So inorganic acids like HCl, sulfuric acid, phosphoric acid are strong acids. Alkyl sulfonic acid is the only organic acid that is a strong acid. Good acids have a pK value between 0 to 12. Examples of the compounds that are considered to be good acids are phenols, carboxylic acids, thiols. Even this methylene group attached to an ester and a carbonyl group is pretty acidic. Weak acids have a pK value of between 13 to 19. Water, hydrogen sulfide, alcohols are considered to be weak acids. What's important to remember is compounds that have a pK value of more than 19 are not acids. Example is ethane, or compounds with double bonds or triple bonds, or the CH2 group next to a nitro, or a ester group or a keto group are not acidic enough. Within a class of compounds, the pK value will change based on the 6 factors. So the class can be an amides or esters or amines. So Lewis acids can accept electron pairs, and so they are called electrophiles also. Common examples are borane, carbocation is a Lewis acid, ferric bromide, and aluminum chloride are another examples of Lewis acids. They all can accept electron pairs, and so they are good electrophiles. Lewis bases, on the other hand, can donate electron pairs, and they are known as nucleophiles. Common examples are alcohols, thiols, amines, phosphines, and X negative is halide. You have alkoxide and several different anions. Thank you for watching. Please like and subscribe for more.